Okay, today we're going to do a quick lesson on Newton's first law, or also known as the law of inertia. Newton came up with the word inertia from a Latin word, and basically he just picked that word because it sort of described what he was talking about, which is a change in its state of motion. So quite often you'll hear this law stated as a body at rest wants to stay at rest, or a body in motion wants to remain in motion. It's the same thing. This is his actual way he wrote it, so we're going to analyze the way he wrote it to make sure we understand what it means. So the first part is he's talking about every body. That's not everybody as in everybody in this room. Let's have fun. It's talking about every physical body. So what he means by body is something that has mass. So the key idea is some sort of object with mass. Okay, so a body is anything that has mass. It can be in Earth, it can be in the moon, it can be anywhere, but it has to have some sort of mass. We're not talking about light or sound or anything like that. We're talking about actual physical objects. And obviously, if we have large mass, we would say it has lots of inertia, or large inertia. And if we have small mass, then obviously it's going to have small inertia. But it's also relative. So large mass would have way more inertia than an object with a small mass. Okay, so if the inertia is larger, that means it's likely going to make more of a difference. So, for example, if I said we have a car going down the highway and we have a little small car and it's going to smash into a brick wall, it's going to come to a stop. It's going to want to keep going forward, so the car is going to do some damage. If we had a big, huge semi, it's got way more mass, so we would say it has way more inertia. So when that thing hits a wall, it's likely going to plow through, or it's going to want to not stop as easy as the lighter mass object. So lots of mass, more inertia; less mass, not so much. And if we're comparing the two, obviously the larger inertia is going to win the battle. So if you have a little tiny car that hits a semi, the semi is just going to plow straight through. It's probably not going to slow down at all and keep going in the straight line direction, where the car is just going to get bounced away and pushed aside like a pinball. So that's the first part. The second part of the sentence that's important to understand is if it wants to continue in a state of rest or in uniform velocity. So that means an object that is stopped wants to stay stopped. Okay, so for example, if you have a person that is in a car and you're stopped at a red light and somebody comes and hits you from behind, your body is stopped inside the car. You want to stay stopped. So after you get hit and your car moves forward, your body's going to move backwards. So it's sort of the whiplash effect. So whiplash in a car accident is basically just due to inertia. So your body wants to stay stopped. So when you get hit from behind, your body moves backwards and your neck whips back, and that causes the whiplash. The opposite is if you're in motion. So let's suppose you're driving forward and you're moving at a constant speed and you hammer on the brakes. You're sitting in the car, you're going to lunge forward because your body wants to keep going forward. So the whole idea of inertia works both ways, and it's sort of a key feature in when they design amusement park rides, right? So the thrill of the ride is having lots of changes in inertia. So your body wants to go one way and the ride goes the opposite, or it wants to stop and it thrusts you really fast to go fast, or you're moving fast and you come to a stop, and so on. So all these changes in inertia, whether in direction or in speeding up, slowing down, all those kind of things affects the inertia, which is what your body can sense. The next part of this graph or description that's important is the straight line idea. So when it's a straight line, that means you want to keep going at the same speed. So for example, let's imagine you whip an object around in a circle, like you have something tied to a string and you whip it around and around and around in a circle. As soon as you let it go, it's going to continue in whatever direction it was going at that split second. So if you let it go at a certain point, it's going to get launched out at a straight line. Okay, it's not going to turn, it's not going to keep spinning, it's just going to get flung at a straight line. So the same thing sort of applies if, imagine you're in a car and you're going to go around a corner like the Thorsby corner. So if you're driving forward and the car turns, the people inside the car want to keep going forward, so you sort of kind of keep going in that direction, so you sort of get hugged, your body gets pushed up against the side of the car because the car's turning, but you want to keep going straight. Or if it was icy roads, you turn the tires, but if there's no friction or force to cause it to change, your car is just going to keep going on straight and hit the ditch. So kind of two different ways to explain the whole straight line idea. Though, unless there's a force that can cause it to turn directions, it's just going to keep on going perfectly straight. And a good example of that too is if we took a glass of water and we put a cover over it, and let's suppose we use like a little toilet paper tube or something, and you put an egg on top. The idea is if you knock that card out of the way, the egg is going to fall in a straight line. It's not going to go move sideways. The egg is going to drop straight down and land inside the water. And you can try that experiment. It works pretty good. It's the same sort of idea why we whip a tablecloth out from underneath the food. The plates and everything, they stay the same place because they're going to stay in a straight line. They're stopped. They want to stay stopped. They're just going to move straight downwards. They're not going to move sideways. Okay, and our last one on here is external force. So the key to that idea is for a change to happen, the only way the inertia is going to change is if we put a force on it externally. So that just means there has to be something to change it. So when we're talking about the car question, if the roads are icy, there's no external force on the tires, we're just going to keep on going straight. If the roads are dry and the tires make contact, then the frictional force will cause us to make the bend, right? So that it'll stay in the same path unless there's an external force. Another good example to think about is you're inside your car and suppose you get stuck, so you tell your friend to get out and push the car. Well, if they're sitting inside the car pushing on the dash, they're adding force to the car, but because they're within the car, nothing's going to happen. They have to actually get outside, stand on the ground, and then push against the car to give you some force that's going to be useful. So the force has to be external, applied to the object to be able to either get it to move if it's stopped or get it to slow down and come to a stop if it's already moving. So that's it for Newton's first law. There's a couple of videos or a video link posted below. Watch that. There's lots of good examples and little cool tricks that you can do with inertia. And tomorrow we'll look at Newton's second law and how they kind of work together.